Hello, you're looking at an applet written by Forsted. It provides us with a mental picture of what an ideal gas looks like. So one of the assumptions of the ideal gas is that the gas particles themselves occupy negligible volume, meaning the gas particles should be very tiny. Of course, the applet cannot draw them so tiny, right? If it's so tiny, we will not be able to see them. That's the reason in the first place why we can't see the gas particles around us, right? The other assumption of ideal gas is that it consists of a large number of gas particles. Large number, how large is large? We can use the equation of state PV is equal to nKT. We can substitute pressure to be 1 atmospheric pressure. Temperature, well, let's use 300 Kelvin. And volume, let's use 1 liter. You get the number of molecules to be 2.4 times 10 to the power of 22. That's a humongous number. Of course, the applet cannot simulate so many gas particles. I don't think we even have enough memory chips to track the motion of 2.4 times 10 to the power of 22 gas particles. But as an applet, I think this is enough for us to have a meaningful visualization. Now, having a large number of gas particles is a very important assumption because statistics works only if the numbers are large. For example, we know that a gas exerts a pressure on the walls, right? So if we have very few gas particles, then actually the pressure experienced by each wall is not constant. It's only when you have a large number of gas particles, then the pressure exerted by the collisions of the gas particles will be constant. Let's move on to the next assumption, that the gas particles are in random motion. Random motion means they travel in all directions. This is a very sensible assumption because if the motion is not random, meaning if there's some bias for the motion to be more in one direction than another direction, then the pressure exerted on these four walls will not be the same. Another assumption is that there's no force exerted on the gas particles except when they collide with the wall or other gas particles, and the duration of collision is very short. And this applet, I think, is written based on that. So you see all the gas particles moving along in a straight line. They change direction abruptly when they collide with the wall or other gas particles. Now, the most interesting assumption to me is the assumption that the collisions are all elastic. Now, notice that the gas particles are color-coded by their speed. Down here, it shows the distribution of the gas particle speed. So the blue ones are the slowest ones and the white ones are the fastest. So the gas particles actually do not have a uniform speed. There's a distribution of speed. Some are traveling faster than the others. If you look carefully, then you realize that when they collide with the wall, they will rebound with the same color, with no change in color, because the collisions are elastic. So the gas particles do not lose any Ke. That's why they don't change color when they rebound against the wall. But when the gas particles collide with one another, you see the color change after they collide. During a collision, one particle may gain Ke and the other one lose Ke. That's why the colors change. But we know that the total Ke does not change, meaning the total amount of Ke of all these gas particles here remains constant despite all these collisions. Now, since we have such a wonderful applet here, I'll just try to show you more things. Now, we can increase the temperature of the gas by heating it. So you can see that when the gas particles rebound off this hot surface here, that's the heater. They rebound at a speed higher than before they collide with it. As a result, the average Ke of all these gas particles will increase over time. That means the temperature of the gas increases. Remember, the average Ke of the gas particles is the temperature of the gas. And you can imagine the pressure exerted on the four walls is now higher because the collisions are more frequent and also the collisions are harder. Now, this applet also allows us to have two different types of gases in the same space. So let's choose that option. So can you see two different types of balls now? So maybe the blue balls are maybe oxygen, O2 molecules, and the smaller ones could be, let's say, H2, hydrogen molecules. Do you notice something about the speeds of these two types of gases? Yeah, the tiny balls seem to be moving faster, right? So this applet is written correctly. Even around us, the hydrogen gas molecules are moving at a much faster speed than, say, the oxygen molecules. And carbon dioxide molecules will be moving at even slower speed. Now, you should know why that is so. I'll give you a clue. The two gases are at the same temperature. So if you think you know the answer, why not just write it in the comment section. Alright, that's all. Ta-ta!